used to make this presentation. My topic is portrait relighting via deep reinforcement learning. This paper proposed a method that uses a deep reinforcement policy gradient to relight portrait. It can edit strokes of local light in a sequence using strokes to dodge and burn light and shade the image. My topic has 4 parts. The first is introduction. The model aims to simulate image editing to make it look like artists use brush strokes. RLPortrait model can produce portrait relighting by sequentially predicting local light editing strokes and use strokes to conduct dodge and burn operations on the image lightness. The core of the method is adopting deep reinforcement learning with deep deterministic policy gradient to train agent. The method can generate location rewards to guide the selection agent to run and relight like an artist. The method is effective, scale-invariant, and interpretable. It can relight portrait images in high resolution. The paper presents 2 groups of experiments. First, a source image and lighting, and second, a source image and reference images. This is my agent robot. Let her accompany with us into the world of science and technology.
We apply the method to relight a face, but something happened. On the negative side, the face has a complex geometry with various appearances, poses, and expressions. On the positive side, the face has a similar regular shape and is symmetrical. We present 2 groups of experiments. First, a source image and lighting, and second, a source image and reference images. We adopt a source image and lighting as input. The top 2 examples are relighting based on lighting. We adopt a source image and reference as input. The bottom 2 examples are relighting based on reference image. This is our system. The agent needs a portrait image and the desired light to produce a new image with the desired light condition as the output. State contains the relighted image and the target lighting condition. Actor network predicts actions based on the state. This action contains the parameters of the stroke. The action is transformed into a soft stroke mask by a pre-trained soft rendered network. The soft stroke mask defines the location of the stroke and the level of adjustment defined within the range of 0 to 1. Then, the image is edited by applying the dodge and burn operations according to the constraint of the stroke mask. Next state is obtained by updating the image. The reward is obtained based on the current state, the next state, and the process of the course to find stroke sequence. The critic network can learn the Q value based on the state, the next state, and the reward for the chosen action. The actor network updates the prediction of the action selection based on the output of the critic network. This is our agent model. Agent model is designed by the DDPG algorithm. It consists of 2 different neural networks. Actor is policy-based. It can output action according to the input state. The critic is value-based. It can be trained via the reward feedback calculated from the states and output a Q value according to the action chosen by the actor. To update the Q value by considering the current reward and next max Q value in the memory until all Q values reach convergence. The actor is updated to expect predicting actions with a high Q value estimated by the critic. This is our action space. The method can relight a local light, so the action needs to define how to adjust the light and where to edit. Therefore, an action is a set of parameters. It can control the position, sharpness, and lightness of a stroke. Use smooth curves to represent the shape of strokes with thickness to simulate the effect of brushes. We represent a stroke curve as a quadratic Bezier curve and control the curve by 3 points with coordinates as seen. Stroke thickness is controlled by two parameters, T0 and T1. The T0 is the thickness of the start point, T1 is the thickness of the ending point. The lightness of the stroke is controlled by the lightness at the start point E0 and that at the end point E1, which have values ranging from 0 to 1. This is our image details. The image details consist of stroke renderer and dodge and burn. A stroke renderer is designed as a neural network. The network can convert the parameters in action to a stroke on a canvas. The soft stroke change from entry to the boundary is generated by gradually reducing the lightness from center to boundary. Dodge and burn can edit the lightness distribution curve of the image. These different curves can be used to influence pixels at different levels. This is an illustration of the effect of dodge and burn. On the left, the dodge curve increases the lightness values. On the right, the burning curve decreases the lightness values. The reward evaluates the predicted action of the agent for the agent to find the optimal action. When the relighting result at the next state is closer to the target image than the relighting result at state, the agent gets a positive reward, otherwise, the agent receives a negative reward. This is our application. Transfer the lighting conditions from a reference portrait image to an input photograph. The agent takes a source portrait image and a reference portrait image as inputs. It requires the source, reference, and target images to train the agent, but the real target relighting image is unavailable. Therefore, we can only calculate the patch gain and stroke rewards. The lighting condition can be extracted from the original image and the reference image using a division method and coarsely transferred to the source image to acquire the coarse relight image. This is our experiment. The method is applied to the shush lighting. These are the source images, these are the target lights. This is our method, these are the existing methods. According to the experiment, my method is state-of-the-art rather than existing methods. The method is based on reference images. These are the source images, these are the reference images. This is our method, these are the existing methods. According to the experiment, my method is state-of-the-art rather than existing methods. In additional comparisons, we compare RLPortrait with our method. The source images in the first column are taken in an office environment. In the image pairs of the middle and right columns, the left image is the result achieved by our RLPortrait method, and the right image is the result by RLPortrait. This is our conclusion. Firstly, the paper proposed a locally compelling, scale-invariant, and interpretable portrait relighting method by modeling portrait relighting as a sequential local light editing process. Secondly, the agent can simulate the artist's relighting process to generate coarse-to-fine actions. Thirdly, the RLPortrait method outperforms the existing state-of-the-art approaches in generating locally effective and interpretable high-resolution relighting for wild portrait images. Thank you for listening, and long press the like button.